So welcome back once again for this hands-on training session. There is no softwares for performing this gray relational analysis. We have to use the simple Excel sheet. In MS Office, you have to use just this Excel sheet to determine the gray relational gray, and from there we can use the Minitab software for drawing the interaction plot or the main effects plot and to make Anova. So the first example that we are going to look is the frictional weld speed. So I am going to just copy and paste the values which I have. Okay, this is my input. This is my input. Next, I am going to have my output. Next, I am going to have my outputs. So these two are my outputs. So these are my inputs and outputs. So the input is formulated based on Taguchi's orthogonal array. Based on Taguchi's orthogonal array, that is L9 orthogonal array. And based on that, the experiments were performed. The experiments were performed and the outputs were recorded. Now, the first step in gray relational analysis is to carry out the normalizing sequence. The normalizing sequence. To carry out the normalizing sequence. Right. So for this, I am going to use the formula for lower the better maximum value of this 9 readings minus individual value divided by maximum minus min. So first of all, we have to calculate what is the maximum of these outputs. For tensile strength, I have to determine the maximum minimum values. For hardness, I have to determine the maximum minimum values. So it is simple formulas that we are going to use. Just to select this two. So here you have this auto sum, no? Just to click this drop button. Here you can see max. So this is my maximum and just click minimum. So this will be my minimum. So now I have determined the maximum and minimum values. So I have determined this maximum and minimum values. So now I am going to use this formula. So in this normalizing sequence, so in the normalizing sequence, the tensile strength has to be higher or maximum, because the tensile strength of any metal should be higher and also the hardness. So I have to use the formula that relates to the higher the better concept. So I just paste the formula here so that everyone can see. So this is my formula. So I am going to just paste this formula here. So xi of k, that is the individual value. So which is equal to, I am going to select the individual value. Just to paste the cursor here. So you have to use an equal sign. Then only it will take as a formula. Then open bracket this. That is the individual minus what is the minimum value of tensile strength. The minimum value here is 234. So just type this 234 divided by the maximum value is 281 minus 234. So now come across this formula. X naught of I, that is the individual value. Individual value is E phi. That is E is the column and phi is the row. So E phi minus minimum of tensile strength is 234 divided by maximum of tensile strength is 281 minus minimum of 234. Just give an enter. That's all. So now you can just copy this and then we can paste. We can paste. If I want to check for the formula, here you can see the formula. So now this E6, E5 alone will get changed to E6, E7. Just place the cursor here in this box, just move this. Now you can see here this E6 is changing. Now E7, E8, E9, E10, but all the other values remains the same. So we have done the normalization sequence for the tensile strength. Similarly for hardness, the hardness is also maximum. So same formula, which is equal to the equal opens the formula. If you don't use equal, the formula will not be accepted. So which is equal to, so hardness is this, the individual value of hardness minus what is the minimum value? 104 divided by the maximum value is 169 minus 104. Just give enter. Just to copy this and paste. So now you can keep the cursor here. You can keep the cursor. So here you have the formula that is here. So it is F5. Now move the cursor here. So it will turn to F6. So here you can see F6, then F7, F6. So all the formulas are correct. The next procedure is determination of deviation sequence. Determination of deviation sequence. So the deviation sequence is nothing but how much these values deviate from the ideal value of 1. So for tensile strength and hardness. So 1 minus, so you have to give equal the formula. 1 minus how much tensile strength varies. So 1 minus G5. Just give enter. So just to copy and just to paste. Similarly for hardness, which is equal to 1 minus how much this hardness varies from the ideal value of 1. Hardness 0, which is equal to 1. That is 1 minus 0 is 1. Similarly in this category, tensile strength is the deviation sequence of tensile strength for first experiment is 1 minus 0.723. It is 0.276. Now copy this and I will paste. Now the deviation sequence is also over. Then comes the third procedure, that is determination of relational coefficient. Determination of relational coefficient, and this one is for tensile strength and this one is for hardness. So for this I have to use the formula provided here. The formula that is provided here. So del min is nothing but 0. The minimum of this value. The minimum of this value is del min, and del max is the maximum of this value. The minimum value of this deviation sequence is 0, whereas the maximum value of this deviation sequence is 1. The eta value is 0.5. Someone asks, so what happens when we can consider different values? We can consider different values, but we have to justify why you have taken this value. For my problem, I have taken 0.5. That may be or may not be suitable for your problem. So you have to justify why you have taken different eta values. So that can you also justify, and it should be based on some references. The references shall be carried out or be taken from some other references. So which is equal to del min. Del min is 0 plus, again I am going to open and bracer, eta value is 0.5 into is asterisk into del max is 1, 2 divided by Once again, I am going to open in bracket del 0 I of k, that is the individual value. So this is the row number 5. So I have to consider this value, deviation sequence value of tensile strength. Just click it. It comes I5, that is ith column, row number 5. So this value plus open another bracket 0.5 into del max. The del max is 1. First bracket, second bracket. Just you enter. So this is my value. I check the formula once again here. Del min. The formula is del min is 0 plus 0.5 of del max. 0.5 of del max is 1 divided by the individual deviation sequence value. That is I5. That is ith column, 5th row. So that is this value I5. So I5 plus 0.5 of del max. 0.5 of del max is 1. Just to copy this, just to paste. Now you can see it is I5. Now you can see it as I5 here. Now I am going to move the cursor down. It will change to I6. Now further changing, it will change I7, I8, I9. So I have given all the formulas. Similarly for harness, I am going to give the same formula equal to del min is 0 plus another bracket, eta value is 0.5 asterisk del max value of 1 divided by the individual deviation sequence value for harness. This is the first trial number 1 plus another bracket 0.5 of 1. Just enter. So I will check the formula here. So minimum del deviation sequence minimum value is 0 plus eta value of 0.5 into maximum value of deviation sequence is 1. J5, that is jth column, 5th row, that is this value, that is the first experimental value of deviation sequence of harness. Now just copy this and paste. So I have calculated the gray relational coefficient values. So I have calculated this gray relational coefficients value. Now I am going to find out the gray relational grade, the final grade value. So we take it as G or gray relational grade. So now I am going to consider this two, average. So which is equal to average of, just select these two. It will give this value, or I can give weightages also, which is equal to, now I am going to give a 0.6, 0.4 weightage. I want a higher tensile strength, so I am going to give 60%, that is 0.6 into the tensile strength plus 0.4 into harness. Put together it should be 1. The weightages should be 1. So just to copy this and just to paste. That's all. Now this is weighted. So give the name as WGRG. So weighted gray relational grade. And this is the general gray relational grade. And up to this, the gray relational analysis is over. So up to this, the gray relational analysis is over. Now how to determine the ideal conditions from this gray relational grade? So for this, we require the Minitab software for drawing the main effects plot based on the response table. So first I am going to just copy and paste. So these are my inputs. So for any analysis I need an input. So these are my inputs, and I am going to use both this for your understanding. I will use both this. So check whether all the 9 rows are filled. Now go with stat, go with Anova. At the last we have the main effects plot. So click this. So the response is gray, relational gray, and my factors are the inputs, the rotational speed, welding speed, and axial force, and I'm going to give OT. So the main effects plot was drawn. So from this, I can identify that the rotational speed of 1800 is my optimum condition, and welding speed of 30 millimeter per minute is my optimum, and axial force of 8 kilonewton is my optimum. Now how to formulate? So this main effects plot is formulated or drawn based on the response table. Now I have the main effects plot, but I don't have the response table. So how to do? So here I will highlight. So check the rotational speed. The first three are the level value is 1. So this first three are level value is 1. Just I have to put the average. So at the bottom you can see average, count, sum, and all these things. So our average is 0.601. Go back to this, we can find out 0.601. So keep your cursor at this point that corresponds to level value 1. So 0.601. Similarly, for rotational speed, level value 2, for level value 2, I am going to calculate the average value. So that will be around 0.482. On the bottom you can see in the Excel sheet, average, count, sum, and all these things. No, average is 0.482. So you keep the cursor at the bullet. So 0.482. Similarly, for welding speed or axial force, I will take. For axial force, for the first level of 6, I will consider this 6, 6, and 6. That is first trial. So I will eliminate this now. For first trial, then 6th trial, and then 8th trial. Now I am going to select, just to press your control button and select the 3 cells. Here you can see the average 0.558. So in axial force, first level 0.558. So the response table is formulated by considering the level values and the corresponding relational grade. So don't get mixed up with this. Just point your cursor over that bullet and you will have that response table value. So you come from this we can determine the response table value. For this is the response value for table value for level 1, level 2, and for level 3. Just take a note of that and formulate the response table. Now, how to draw the interaction plot for this gray relational gray? Start. Once again, Anova. At the last, we have the interaction plot. Yesterday also we have seen that gray relational gray and all these 3 inputs and display full interaction plot. So this is how we are going to obtain the interaction plot. So here, so this is the rotational speed here, and this is between, then this is between, drawn between the rotational speed and the welding speed for different rotational speeds. But this second row, first column, this image is drawn between rotational speed and welding speed for different welding speeds. So that's the difference. So that's why we can identify what is the interaction effect for different cutting speeds or rotational speeds and for different welding speeds. Now, Anova. We have to formulate Anova. Someone asked in the morning, sir, we have determined which has the highest influential parameter from the main effects plot itself. Then why we are going with Anova table? Only from the Anova table, the variance that exists between 2 parameters can be studied, and the percentage contribution of each and every parameter can be determined. And which with the confidence interval, because we are going to perform this Anova based on 95% of confidence interval. So what is the R square value that we are going to obtain? Whether my model is a fitted one, whether my data is a better data, that can be obtained only from this ANOVA. So stat ANOVA, here you have the general linear model. So fit general linear model. The response is grade relational grade, and the factors are the inputs. Just click OK. So the Anova table is formulated here. That is with an R square value of 99.69. The regression coefficient value, the ideal value of regression coefficient is 1, and we have ended up with 9969, 0.9969. So it is very a good model. Now someone asked, sir, this is the main effect spark for grade relation grade. Now you are given some weightages. The weighted grade relation grade, we are given a weightage of 60 to tensile strength and 40 to hardness. Now what influence this will make? That also we can study. Now stat ANOVA main effects plot. Now instead of grade relational grade, just delete. I'm going with weighted grade relational grade. Now here, this is the comparison. This is the comparison of this. So with the change in the tensile speed, tensile strength, the optimum condition varies. You can see now. With the equal weightage, the hardness values influences more than the tensile. That's why the optimum value is 1800. But here in this case, the optimum value is 1000. The rotational speed, the optimum value is 1000. The welding speed is 30, and the axial force is 8. So the weightages does not have any impact on welding speed and the axial force, but it has the impact on the rotational speed. Okay, on what basis we have to choose that weightage? So for each and every experiment, we should justify why we have taken this much amount of weightage. Because here in some applications, so we have taken two outputs, that is the tensile strength and hardness. In some applications, the hardness should be high, so that may given a higher weightage. In some occasions, the tensile strength will be given much importance. So in that cases, higher tensile strength, that is the weightages will be given to tensile strength. So it depends upon the application. So we are going to perform some research based on some applications. So for that application, the weightages should be formulated by you, and you have to justify that in the research manuscript. So hope you have learned how to execute this grade relational analysis in the Excel sheet. So now I will go with the next example, that is hybrid Taguchi based optimization approach. The hybrid Taguchi grade relational analysis. So for this, we have considered the L16 orthogonal array. So that input values I am going to choose. So that input values I am going to select. And further, the corresponding output values I am going to have. Right, these three are my inputs. These three are my inputs. and these three are my outputs. So in Taguchi based analysis, the first thing that we have to do is determination of SN ratio. Determination of SN ratio. And the next category is normalizing sequence. And the next thing is deviation sequence. Then determination of relational coefficient. Then gray relational gray. So this is my procedure. Then this is thrust force. I'll give you the full wordings. Thrust force, torque, then MRR. This is a common index. Right. Now, how to calculate the SN ratio? No issues. Just copy this and go to Minitab. Go to Minitab. Just paste this. Just paste this, because SN ratios we have to determine. It has some formula. So directly from this I can determine. So go to Stat, DOE, Taguchi, Create. So I have created. So go to Define. My inputs are these three as my inputs, because this design is based on Taguchi. That's why we are not once again going to create, but we have to define which are all the input parameters. Then Stat, DOE, Taguchi, Analyze. But my aim is not going to analyze, but my aim is to determine the signal to noise ratio here. So first torque graph. I know don't need any graphs. If you want, you can analyze individually. That also you can include. Analysis. No response tables. Terms, single terms. The options. So this is very, very important here, because from here only we are going to consider this. Here the thrust force should be minimum. The thrust force should be minimum. So torque should be minimum and MRR should be maximum. So that is our aim. So our aim is to have a minimum of thrust force, minimum of torque and maximum MRR. So torque and thrust force, it should be smaller is better, and the storage is signal to noise ratio. Okay, then okay. So this is the signal to noise ratio for thrust force. So just to copy this and just I am going to paste. Just I am going to paste. The second one, Stat, DOE, Taguchi, Analyze. I am going with the torque as my response and check with the option smaller the better, then okay. So this is response to SN ratio. But also I am going to copy and paste. Now comes the third category, that is the MRR. So DOE, Taguchi, Analyze. Now I am going to determine the SN ratio for material removal rate, which should be higher. So I am going with larger the better formula. I am going with the larger the better formula. Okay. That I am going to copy and I am going to paste. So I have determined this one. Now I am going with the normalizing sequence and all these things here. Now normalizing sequence. So what is the formula for normalizing sequence? So I have to determine the formulas here. So this is for larger the better. So this is for larger the better. And for lower the better, it should be this. I'll put it in the first category. So this is for thrust force and torque. I will fetch it here, no issues. So this is, the first one is for minimum and second one is for maximum. So the initial step in normalizing sequence is to convert all the data values in between zeros to 1. So for this we are going to use this value. So for this, the initial step is to determine the maximum and minimum value. So I am going to determine the maximum and minimum values. So which is equal to, so don't go with this, just to copy, select all these three, go with the auto sum, drop menu, maximum. So we have the maximum, then we have the minimum value. So that's all. We have the maximum and minimum value. Now thrust force. Normalizing sequence, the thrust force, the formula is this. So for smaller the better, the formula is maximum minus individual divided by maximum minus minimum. So this is for the minimum. So which is equal to the individual, the maximum value. The maximum value for thrust force is 30 minus 32.608,761 minus the individual value for thrust force divided by the maximum minus minimum, minus 32.608,761 minus of minus becomes plus, because the minimum value is minus 53. So minus of minus 53.30676. So it comes around this. So it comes around this value. Whether the formula is correct or not, that we can check. Just copy this and just paste. Now similarly for torque, which is equal to maximum value is 14.199, 14.199, 3078 minus the individual value of torque divided by the maximum value 14.199, 3078 minus 19, that is the minimum value, minus 19.488391. Just to copy and paste. Just to copy and paste. And MRR, which is equal to MRR, for MRR, the second formula that we have to use. The individual value minus minimum value. The MRR, individual value minus the minimum value. The minimum value is 20. 20.0389988 divided by the maximum value is 45.399502 minus the minimum value is 20.0389988. Everything is clear? Now we are going with the deviation sequence. So which is equal to 1 minus, that is the ideal value is 1. So how much these values deviate from this, that we are going to provide. Which is equal to, for torque, 1 minus the normalization sequence of torque. Which is equal to 1 minus torque. So obviously these three readings are 0. So obviously these three readings are 0. So just to copy this and just paste. So this is the calculation for deviation sequence. Now coming on to the, so this is the relational coefficient value. So now I am going to use this value. So this is the formula for relational coefficient. Eta I of k is equal to del min plus eta del max del by del 0 I of k, that is the individual deviation sequence value plus eta del max. So for thrust force, which is equal to the minimum value is 0. The minimum value is 0 and the maximum is 1. So actually this is the minimum value. Actually this is the minimum value. So here you can see 1 minus 999. It is the 1 value. Here you are able to see this. I hope so. So this value is 0.999. So 1 minus this value will be 0. Similarly for the other things, this is 0 because this is 1. Am I clear? So this is similarly. So these three are the 0 values. And this is the 1. Values of 1. That's for gray relation analysis, which is equal to the del min is 0 plus other braces 0.5 into del max of 1 divided by the individual value of thrust force. This is this plus 0.5 into 1, that is del max. Just enter. Just to copy this, just to paste. Similarly for torque, which is equal to the del min is 0 plus bracket 0.5 into 1, another bracket divided by the individual value of torque plus bracket 0.5 into 1. Just copy and paste for the remaining experimental trials. For MRR, which is equal to 0 plus 0.5 into 1 divided by the individual value for thrust force. This is 1 plus another bracket 0.5 into 1. Enter. Just to copy and paste. Now here comes the gray relation grade, which is nothing but the average of all these three things. So just equal to average, just to copy this. So Q5 to S5. Copy and just enter. Now you can copy this also and then you can paste. So here you can see so initially we have calculated the SN ratio. So initially I have calculated the SN ratio, then I have calculated the gray relation normalizing sequence, then deviation sequence, then gray relational coefficient, and finally I have determined. So here in the SN ratio you come across many terms, so I am going to reduce it to 3 digits. So select all these values, and just right click, format, so numbers, so decimal places is 3. So decimal places is 3. So here previously in this category it is e power something. It is e power something, and now it has become 0 because of the decimals that we have used. So use it up to 3 digits. Now what to do? Just to copy this gray relational grade values, because we have to determine the optimum or the ideal conditions. So for this we have to formulate the response table, and then we have to draw the main effects plot. Then to study the interaction effects we have to go with the interaction plot. Then to determine the percentage contribution, whether the fitted model is perfect by using the R square value, we have to go with the ANOVA. So Once again, I am going back to this mini tab. Now, in the column C10, I am going to type it as relational grade. In column number 10, and I'm going to just paste this value and check whether all the 16 values are filled. Now I am going for the main FX plot. Don't go once again with Taguchi's analysis because I am not going to calculate the SN ratio. My aim is to determine the optimum condition, so I am going with the main FX plot. So stat Anova main FX plot. The response is relational grade, and the factors are my inputs: surface speed, feed rate, and drill bit diameter. Okay. So this is my conditions. The optimum condition is surface speed of 30. This is the lowest level value, and feed rate is the highest one, 0.1 millimeter per revolution, and drill bit diameter of 6. The drill bit diameter of 6. Now we are going to study the interaction plot. So Anova interaction plot, the response is relational grade, and the factors are the 3 input factors. Display full interaction plot, that checkbox I have to tick, then OK. So here you can see in between surface speed and feed rate, and also in between surface speed and drill bit diameter, a considerable interaction exists. But in between feed rate, this graph is drawn between feed rate and drill bit diameter, and mostly it is of parallel lines, so no interaction exists. So that's we are going to conclude or interpret here. And now we are going with the Anova table, because which contribution is high, that I am going to determine. So go with Anova general linear model, fit general linear model. The response is relational grade, and the factors are my inputs: surface speed, feed, and the drill bit diameter. Then just click OK. Now I have my Anova table here, and the summary. The model summary speaks about the R-square value and R-square predictor. The R-square value is 95.05. So I'm just going to copy this Anova table. Copy. Now once again I am going to come back to this Excel sheet. Just paste this. And now I am going to calculate the percentage contribution of each and every input parameters. So which is equal to the percentage contribution is calculated by dividing the sum of squares of individual with the sum of squares of the total, which is equal to the sum of squares of individual. This divided by the total is 0.404318. So just to copy this and just to paste this. Now select this. Here you can have a percentage. So percentage, how many digits? 2 digits. So the influence of drill bit diameter is higher. So the ranks 1. And the influence of feed rate is second. The influence of feed rate is second. So it ranks 2. That's it. So this is the hybrid approach of merging both the advantages of Taguchi's technique and the multivariable analysis or multivariable optimization of grade relation analysis. So put together, the efficiency of this analysis is well improved. So finally, with the obtained optimum condition, we have to carry out a experimental study. And then we have to validate. The results. And then only we can tell whether this approach is perfect or not. So for prediction, we have to use the formulas that we have seen in Taguchi's optimization method, and we can also predict what will be the final relational grade of the validation experiment. After performing the validation experiment, we have to calculate the relational grade of that optimum outputs. by initially calculating the SN ratio of that outputs, then go with the normalization sequence, the deviation sequence, and then regression coefficient just by entering this value. For example, if I'm going to obtain a value, so now I'm going to change this one. Now I'm going to change this one. For example, because now I have performed the validation experiment, I have got some readings. Now, how to get the GRG? Just for example, instead of 217, I am having 317.102 like this. 312.104. This is my optimum conditions, and for torque it is 2.517, and for MRR it may be 103.567. So this is the ideal conditions, but we have to change this value also, because this is copied from Minitab. Now this might not have changed. This might not have changed. So for this we have to calculate the SN ratio, and that SN ratio only we have to enter here, because automatically it will not change. So we have to change this value. So for example, I'm going to consider instead of 46, I'm going with 42. So here you can see, just to force this value 6.68 will get changed now. This change to 0.490. So change this SN ratio based on these values. So I will have an grade relational grade value. So that compare it with the predicted value. Precisely these two values, the predicted and the experimental GRG values, will be close to each other, because we have gone for the advantages of both the Taguchi's approach and grade relational analysis. So the predicted and the experimental results will be nearby only. And this is how to work out this grade relational analysis in simple Excel sheet and to perform the hybrid Taguchi grade relational analysis. I hope each and everyone will work this so that you can produce some good papers in the near future. And with this, I stop this session, and the next section will be at exactly at 2 o'clock, which we are going to look into some of the basic concepts of principal component analysis. And that I will tell you how the principal component analysis can be incorporated in this grade relational analysis, and what is the advantage of the principal component analysis, and how to work that on the softwares. So now the session is open for chatting. So we'll see then. Thank you.